How you guys doing? What's going on? How are we feeling? Oh, great. All right. Little
Same.
getting closing down, final countdown for this semester thing, whatever it's called, quarter. What do you guys call it? Term. All right. Final stretch, right? So I think we only have 4 classes after this. And you've probably realized where the textbook is gonna probably cover a bunch of stuff we're not gonna make it to. I made like a short list of things I want to hit in these last 4 classes. We need to talk about these compact objects some more, so the black holes, the neutron stars. Hopefully we can get through the lion's share of that today. I want to talk about galactic black holes and dark matter. That situation is always, that's a fun one. We need to then switch over to cosmology to wrap this up. So we need to talk about the 2 pieces of the Big Bang that are the main pillars, which is the redshift at a distance relationship, the expanding universe, and the cosmic microwave background. So that's it. That's the rest of this course. I wish I could do more, and there's a lot of stuff I'm not going to be able to cover. Hopefully you guys got a good glimpse into that through the Moodle stuff and the workshop and all of that. But yeah, maybe you guys are starting to think more about your final projects too. I'm looking forward to your research, and I really enjoy seeing what people come up with. Last year, some folks did a really incredible job and found new details of this puzzle I wasn't even aware of. So that was really fun. All right, you guys have any like business related questions about stuff? Anybody ready to talk? Any questions about final project or anything? We can talk about it more next couple weeks too. Otherwise, let's keep this party moving. So we need to really round out our discussion of hyperdense objects. I would love to finish that today, but we might have to spill over into Monday because, yeah, black holes require us to discuss relativity a little bit, and that can sometimes be a prolonged interaction. It's pretty far out. I'm going to try to stay away from the intense math because that would be hopeless on a bunch of non-mathematicians, but hopefully we can make conceptual sense of it. So what do we remember from last time? I know that we barely got into white dwarfs at the end, so I'm going to review what we talked about, particularly with respect to the liquid model of stars. Can you guys, well, actually, I always got to remind myself to do this. What is the central crisis at the heart of astrophysics right now, from where I'm standing? Yeah, right.
Whether the sun is a liquid or a gas.
All right, and why does it matter? 3 reasons. Maybe you guys have a 4th one I haven't thought of. Yeah, Evan.
So we are working off of correct knowledge.
Yeah, and who cares? Why do we need to be working off of correct knowledge about
For everything.
something as trivial as the stars? Yeah,
So things make sense
so things make sense.
using incorrect information.
Yes, I think that we're threatened by a deeply superstitious age right now, and we don't want to find ourselves in another medieval period of another dark ages, right? So it would be really wise for us to have a science that's internally consistent, that's reliable, that some mean priest can't come along and tell you that things don't have to make sense, and that's okay. All right, so that's my favorite one. What are 2 other reasons? Yeah.
So we know how the stars create fusion.
Sure, yeah, so we understand how the stars power themselves. We've obviously been trying to do that on Earth for a very long time. It hasn't been working out. Maybe we can learn something new if we approach the stars differently. So that's a good one. And then maybe the 3rd one, which is kind of tied into what we're doing in this class. Yeah.
Because our assumptions of and everything downstream of what the sun is based on what we think the sun is.
Yeah, so it ties into the first thing that we mentioned. So our story of the stars changes completely. Everything downstream of it, all the way to cosmology, which is the meta story of our whole universe, depends on the liquid versus gaseous interpretation of the light that we see shining from these sources in the sky. And who cares about cosmology? Well, it impacts all of science, actually. It's not so easy to see until you start working in a particular form of science, and then you will find yourself confronted with something cosmological at some point, which is pretty shocking, but it is true. All right. So going from there, that's the big picture. Where did we leave off last time? What did we talk about? We talked about the deaths versus the cooling of stars. Somebody remind me of this dichotomy a little bit. Yeah, Kevin.
We were talking about how the kind of more tame version, how the stars kind of died and the, I guess, issues with that.
So tell me about, can you elaborate on that a little bit? I want to know which piece you're talking about. So there's two paths, right? We got a liquid and we got a gaseous endpoint, right? Or course, let's say evolution. How about we just sort of roughly outline those two approaches, maybe?
I think we did.
Yeah. What do you remember?
We were talking about how, you know, how the layers of the lower mass stars kind of drift off when the stars end up running out of fuel, or at least fuel for their size anyway. And
So that's kind of in the standard model. In the gaseous model, fusion's happening at the center. As the stars exhaust their fusion supply, they no longer have the means to, they just no longer have integrity, essentially. And the balance between gravity and radiation and gas pressure is gone, right? And so bad things happen. They lose their outer layers, they collapse upon themselves, which is kind of where we ended up with that. In the liquid model, we also have the potential for the stars to cast off layers, but does anybody remember what the difference is with that approach? You guys remember we were talking about sunspots way at the beginning of the term? What did we point at as a possible mechanism for sunspots under the liquid model? Yeah.
I just remember you talking about the liquid model that they're like stacked on top of each other and stuff can be in between.
Yeah. So yeah.
Impurities, stuff, just impurities in the liquid metal that then, because lattices can have, where the impurities can be in between layers,
Yep.
and then as it's trying to get those impurities out,
Yep.
it can shed off layers.
Yeah. So I meant to pull up a video of this for you guys. So there's a known version of this, right? There's there's some YouTube videos you can watch of this, but actually if you take graphene, which is a layered carbon structure, and you dissolve gas into it, if you actually strike the surface that you've layered the graphene onto with a hammer or something, you can cause an explosive decompression of that gas inside of it, and it rips the layers off, right? So things like this.
Graphene or graphite?
I think these are actually, I'd have to look, actually. That's a good point. Graphene's a tubular structure, but it does actually have hexagonal layers if they're arranged vertically. So you still have hexagonal layers in it. Might have been graphite, actually. I'll see if I can dig that up if I remember for Tuesday. But the same kind of processes is what we're kind of pointing at with the delaminating of stars, right? So in these red giants, and in these, particularly with those nebula that we talked about, it looked like explosions have happened. Of course, in the standard gaseous model, those result from this violent death of stars, and most stars are expected to go through this process. In the liquid model, it's an edge case situation where shocks inside of the star for certain unstable stars can lead to this kind of explosive decompression. So it's more of a stars explode under extreme rare conditions with the liquid model. All stars essentially end up exploding for the most part under the standard gaseous model. Now, we only talked about small, modest-sized stars last class. So after one of these modest-sized stars casts off its outer layers in the gaseous model, we end up with that little dim star at the center of those nebula, right? We took a look at some of those pictures. does anybody remember what's the deal with those little guys under both of these? Because I barely got into the liquid one. Yeah, go ahead.
They're like white dwarf.
Yeah, these things, the white dwarfs. Yeah, what do you remember about white dwarfs from either perspective, either the standard or the liquid perspective? Anybody? Yeah.
From the standard perspective, it's the core of the star, what's left of the core, and the hyperdense core after it's shed all of its other layers, and it's basically running on fumes until it just. I don't know what happens when it goes away, but yeah, it's just there,
Yeah, so the idea is that
and it's also incredibly small.
incredibly small, yeah. So we're talking about the sun, which is more than 99% of the material in our solar system would be crunched into something the size of the Earth, basically, right? So, something that's million times the density of water. It's sort of unimaginable for atomic structures. The only way that the theoreticians get around this is by saying that they're no longer atoms at all, right? These are just particles. At some point, the electrons don't want to touch each other. They don't really bother with what an electron is. It doesn't matter to them. They're just these things that repel each other. And so it's the reason that the white dwarf doesn't just collapse into nothingness, which we'll look at in a minute, is because there's not enough of these particle thingies there. And so they don't have that much mass. Never mind what mass is, but they don't have enough mass to keep doing that. The electrons push against each other. And so they call this a degenerate electron gas that repels it. So instead of the gas pressure and the radiation pressure holding the star up, as it is in the main sequence standard model, we have this degenerate electron pressure that keeps the things at least from eternally collapsing for approximately solar mass-ish stars, so the modest-sized stars. And we're going to look at today what happens when you have huge stars that go through this same process in the standard model. So, okay.
And then white dwarfs in the liquid model,
Yes.
they are slightly smaller than they were before, but they're not like hyper dense, and they're just transparent, basically lower opacity.
Yeah. So,
This is
right, exactly. So again, in the liquid model, this is you could think of this as just the black body equation in general. But in the liquid model, we actually have to contend with some of these other variables, namely the emissivity, right? So the emissivity is the quality of the atoms in the lattice that lets them turn light into heat, heat into light, that lets them produce light, essentially, right? So obviously diamonds are very different than soot. They're both made out of carbon. They have different lattices. That's because their emissivities, that little epsilon term in this equation, is not equal to 1, right? For different materials, different arrangements, different lattices. That means that we can get something that's really dim, can still be quite hot, really dim, because its emissivity has been altered by its new lattice conformation. So we have a different kit of tools available to us in the liquid stars. Again, we have diamond versus graphite shown. Both made out of carbon, just different arrangements of the atoms, completely different optical qualities, right? So that's the revolution that changes your ability to imagine how to explain things that perhaps are very dark and very big still, have a lot of gravity, right? So you no longer have to squish things into a small radius under the liquid model. You can have things that are still pretty chunky, they're just dim, right? 'Cause they don't have very good lattices for transforming heat into light all of a sudden. So what we're really talking about in the liquid model of white dwarfs and everything downstream of that is phase transitions, right? So this is kind of like, you guys ever hear about phase transitions before? Remember this from chemistry at all a little bit? What's a phase transition? Anybody? Yeah, go ahead, Ethan.
It's when matter changes its like atomic structure?
Yeah, it's this. It's lattice rearrangements, ultimately. I mean, at some point, your lattice comes apart completely when you're a gas, right? You don't have any bonding to your neighbors when you're a gas. But it's essentially something that has to do with, it's really just this broad-based term that we apply to what happens when materials undergo transitions in temperature and pressure, right? How do you make a diamond? Yeah.
You take, I'm pretty sure either coal or you take carbon.
Yeah, you take a bunch of
You
soot.
take a bunch of carbon,
Yeah.
and then you compress it a lot.
Yeah.
And have a lot of heat.
Yeah, you do this, right? So you take it on a walk on the phase diagram. And so what we're saying with the liquid model of these compact objects is that they're not really compact. They've just undergone phase transitions that have altered their optical qualities.
They're not as compact.
They're not as compact. They're certainly not something like the entire T of the sun crammed into something the size of the Earth, right? Sure, they have lost layers. And presumably, if what we're looking at in a white dwarf is actually the core of a star that shed its outer layers, it might be more dense, it might be more compact. But it's still atomic matter. It's nothing, it's not some exotic place where physics breaks down or anything like that. And we're going to keep seeing that come up, which is why I think this liquid versus gas model is so much fun for intro science students like you, because what we're really looking at is we're looking at defending the line where science is in some sense under threat, because what's happening in your textbook and what's happening in standard astrophysics for the last 50, 75 years is that the experts have been saying something akin to, well, physics doesn't have to apply exactly anymore in these situations. And that's a really pernicious, perhaps even nefarious assumption for some discipline, an art form like science, where the whole name of the game is to have things be consistent and make sense, right? So that's why this is kind of a fun trial, whether you care or not about the stars. You get to see a situation where things are being brought into at least making material sense, which is the whole game of physics. I'm not exactly sure what physics would do if it didn't make material sense of reality. It certainly isn't going to be telling me about, you know, how to have better relationships with my friends and family or something, right? So its only job is to make material sense of reality. And that's why this is such a cool project to show you guys, regardless of whether you care about the stars or not, or, you know, the ultimate fate of astrophysics. So yeah, so we have these phase transitions. So, you know, in some sense, I pulled this actually out of like a pop sci article, but I think that it illustrates, it's from Scientific American, and it kind of illustrates, in some sense, the two different paths that we're really talking about with the liquid versus gaseous stars, right? So in the evolution of the gaseous stars, they all basically go through this transition where they blow up and there's some remnant left behind that's hypercompact. The liquid stars, they just evaporate. They get cold and evaporate, essentially, for lack of a better word, right? Go ahead.
Well, when you say they evaporate, they don't just turn into nothing, right?
They probably are full of a lot of, like I said, the cores are probably quite solidified, right?
Yeah, so they become planets, is what you're saying, basically.
I mean, it seems like a sensible road to making a planet. Look, like, I think that another sensible road to making a planet would be something that didn't quite become a star in the first place either.
Mm-hmm.
Jupiter's constantly gobbling up stuff. So it eats asteroids, it eats comets, presumably all that heavy stuff from those asteroids and comets, the heavy metals, the nickels, the irons, it's going to get concentrated at the core, right? So you could make something that looks a lot like the Earth at the center of Jupiter too. Now, did Jupiter used to be a star? Maybe. Maybe not. Maybe it was on its way to being a star and it didn't accrete enough matter through whatever circumstances. But maybe it did used to be one. I don't know. It's very hard for me to see the difference, although I think that could be sorted out in the future based on different chemical stories that you would tell. And you could maybe make distinguishing features if this was studied. There's a lot of work to be done in the next 500 years after this renaissance occurs. So All right. Questions, thoughts? And by evaporate, I literally just mean the solar wind, right? You know, under the liquid model, the solar wind is basically just sublimation. It's a very fast form of evaporation. Yeah, I guess maybe evaporation is an even better word than sublimation. But yeah, you're going from a liquid to a gas at the surface. This is something that happens with our oceans all the time. It happens with glass water. You guys are quite familiar with it, I'm sure. All right, so this is the overarching paradigm. Differences in the paradigm for the evolution of these two models. Make sense? All right, so this is actually from the same article, which is kind of fun because, you know, this is a very mainstream magazine, Scientific American, and you can see that we have our HR diagram that we've been talking about, and that's in the textbook all over the place. Over here on the right-hand side, you can see that if you extend it, you can actually fit all your brown dwarfs onto it. And I would add that if you continue to extend this, you can fit all of the planets onto it as well. They would all make like a nice line. So the main sequence actually extends indefinitely and covers pretty much all the bodies that we're aware that we're familiar with, let's say. Let's skip that. So, of course, the mainstream astronomy does deal with stars that are not large enough to even form white dwarfs. They would say that these things would cool off just like we're saying the rest of the stars cool off in general. They become these things called black dwarfs. Oh, I guess these are, I take that back. It seems like these are actually white dwarfs that have cooled off too. So the problem is, why don't we see any black dwarfs according to mainstream astrophysics? Yeah.
We just can't see them. They're too dark.
Yeah,
It's because
Abby, sorry.
we do go off the Big Bang, the universe hasn't existed.
That's exactly right. Exactly. Yeah. So it just hasn't been long enough. So these are supposed to take, you know, maybe trillions of years to cool off. Yeah. I mean,
Under the liquid model, could black dwarfs exist just as a star does not have the material to fuse and create light any longer?
yeah, exactly. So it would be just a Jupiter or something like that. Yeah, or maybe even an Earth eventually. Or a moon if it's been around for a really long time, maybe. And it's just, yeah. So now the interesting thing, though, I pointed this out. I figured I'd just show you a couple frames of it. So, you know, we're going to talk about, so there aren't that many, we don't see a lot of planets doing this white dwarf transition thing, right? Sorry, I said planets, stars. We don't see a lot of stars doing this business, and we don't see a lot of stars going nova, and we don't see a lot of stars going supernova, which is what big stars do, and we'll get to that in a second. What we do see is we see evidence of a lot of stars going dark, which is really, really weird if they're supposed to all blow up first before they go dark, right? And it hasn't been long enough time for them to have gotten cold per the Big Bang story, right? So this is a really interesting piece. I think everybody should go check it out. At least anybody's interested in this stuff. It's called the Vasco study, where a Spanish astronomer has gone through and cataloged all of these old Defense Department images across 30, 40 years of the night sky. And she goes to great lengths to talk herself out of as many of these disappearing objects as possible. Because of course there are reasons, you know, that an object might appear one year and not the next. You know, maybe something got in the way. Maybe it was just an artifact on the film. There's lots of things that you can talk yourself out of, but statistically speaking, you can't talk yourself out of all of them. And so this is a really, really fascinating situation. So
Yeah, often the simplest explanation is the correct one.
yeah, yes, I agree.
I noticed in the 4 pictures, the like bigger star in the square. That I'm assuming that's the one that quote disappeared. But
Yep.
there's like a smaller star in its place.
If you look really hard, it's kind of hard to see here. That smaller star is still there in the upper
Oh,
left.
Yeah, it's right to the just the top right.
Yeah. And I mean, again, she's found hundreds of thousands of these things, right? This isn't so one of the weird things that's always bothered me about this standard story that's in your textbook about that HR diagram is that all the stars are supposed to be going through this transition to the red dwarfs and then to the white dwarfs as they leave the main sequence, right?
You mean red giants?
Sorry, yeah. Giants, the red giants, right? They swell up, lose their layers, become white dwarfs, right? There aren't that many white dwarfs. There aren't that many red giants, right? And so where are all of these things as they're happening? There aren't that many explosions that we see. In fact, we haven't, since the invention of the telescope, we've only seen one supernova ever in our galaxy. That's pretty insane. There technically was one right outside of our galaxy in the Magellanic Cloud, which is like a satellite galaxy that kind of hovers around our galaxy. But they're really, really rare. And that's pretty bizarre if this is kind of the standard story. However, if stars are just sort of stopping glowing because they run out of fuel, which is what we would expect under the liquid model, then there should be a lot of stars just blinking out of existence all the time, right? Which seems to be what we actually see. So that's really, really fascinating.
Kind of terrifying in a way.
Yeah, fair enough, fair enough. Yeah, what do you got?
I'm curious how the luminosity of just the immense amount of stars around our location in the galaxy might affect our ability to see some far off star exploding, because they could be exploding. They could, but maybe we just can't see.
I think they can and they do. And so we do see big explosions in other galaxies. Problem is, other galaxies are incomprehensibly far away to the extent that resolving individual stars in them is problematic. And so we don't, I don't have a ton of confidence in resolving what exactly we're seeing when a piece of a galaxy lights up really bright. I think there is good reason to believe that stars do catastrophically explode periodically. I don't think it's a very common occurrence, though. I don't think that anybody could make the argument that it's an obviously common occurrence. Yeah.
I guess it's mostly a comment, but if we're seeing all these explosions in faraway galaxies, how do we know that's just not some lucky little bit of light that's refracting off of a lucky piece of dust or something?
Well, they're really bright. They outshine the whole galaxy. I mean, it could be a Star War or something. I have no idea, right? Yeah.
I mean, kind of like how the sun can bounce off of the earth. What if it's just a little bit of light that happens to bounce off?
Oh, on the way here.
Yeah.
Yeah. I mean, there are some reproducible effects, right? So we can measure, and I probably won't have time to get into all this. You can study the light curves of these things, right? So how they, basically you can draw some similarities between these events as we see them in different galaxies, right? So there's some reproducible phenomenon that's happening. The same thing is going to be true for black holes. There's a reproducible phenomenon. There's stuff that's weird, right? There are bodies that appear to be orbiting dark places. What's going on? So the apparent phenomenon requires an explanation. And quite frankly, the explosion of stars, it's fine. That may very well be what's happening. The question is, how does that happen? And by what material means does that happen? So the standard story that we're kind of getting to is that for a star that's really, really massive, right? Well, once they go through this white dwarf phase, they actually have, in the standard story, enough stuff to keep squishing themselves together past that electron repulsion, right? To the point, and this is kind of interesting, to the point that the electrons and protons combine and form neutrons. I'm not sure how far I want to get off the path with this, but it's really interesting that neutrons are basically just electrons and protons crammed together. What is a hydrogen atom, by the way?
Electron.
Yeah, it's an electron and a proton too. So neutrons are really, really similar to hydrogen atoms. Actually, one of the most preeminent chemists in the 1800s, his name was William Prout. He was a bit of a drunk and a womanizer and stuff too, so he doesn't make it to the history books very well. But he had this theory, basically, that you could build all of chemistry out of hydrogen atoms, all the atoms, all of everything. They didn't know about isotopes, so they didn't know about the neutron. So when the neutron was discovered, which gives some of the elements, a spread of weights, let's say, he was kind of defeated. But it's a really interesting proposal because, neutrons spontaneously decay after a few minutes into protons and electrons, which, you guessed it, is basically a hydrogen atom. There's a little bit of extra radiation left over we call neutrinos. I think I mentioned this earlier, but there's something really, really interesting there if you think about what it means when radioactive decay happens and neutrons are given off, right? It's almost like a little chunk of the atom is popped off, and it's not fully functional as an atom yet. You can't quite call it a hydrogen, can't really engage in electric processes yet, almost like its surface isn't patterned correctly. But it will become a functional atom, essentially, at least by a counting balance, right, by the particle balance. So that's really fascinating with neutrons. So anyways, the standard gaseous astrophysicists have these ultra-dense objects. Now they're even denser because you don't have that electron repulsion. So you just have more stuff crammed in an even smaller space. And these things, these super compact objects, are called neutron stars. By the way, white dwarfs, I told you they were like 1,000,000 times as dense as water. These things are supposed to be 400 billion times as dense as water. Yeah.
Is that why it's referred to? When I read the word crust, I assume like solid matter. Or
I mean, these concepts start to fall apart is the problem, right? Like, what does that even mean? What does matter even mean at that point? Yeah. It gets really, really weird. Okay, so these are just ultra dense objects. Now, let me make sure I don't have anything else to say about these collapses. Okay, so this is where we get our supernova from too, by the way. So big stars, they collapse. They do that normal planetary nebula type collapse at first. Then another flash happens, and this conversion where those electrons combine with the protons and form the neutrons in this story is extremely violent of a collapse, right? And the result of that compression is that it gives off a tremendous amount of energy, a tremendous amount of radiation, high energy radiation, which blows the thing to smithereens, the outer layers of it anyways. And that's where we get these neutrons. So these are that's where we get these supernova, right? So these are some pictures. Every single one of these pictures is actually from another galaxy that we see this flash in. So these are the flashes I'm talking about, Kevin. I mean, they're brighter, they're almost, they're more particulate, but they're brighter than the entire galaxy, generally speaking, these flashes that we attribute to supernova of this variety, right? Now, there's some interesting features of this, though, right? So do we see anything compact at the center of these? So there's a few, so I should go back to this. I should walk this back a little bit. Never seen we've seen one of these in our galaxy since the invention of the telescope, and this was a long, long time ago, right after the telescope. We do see a lot of explosion-looking thingies, kind of like the planetary nebula, that get chalked up to supernova that may have happened several thousands, tens of thousands of years in the past, right? So we still see the remnants of them in our galaxy. Do we see compact objects at the center of these things?
I'm gonna guess no.
Those are way too far away.
The answer is a very small sometimes, maybe. So we have to start asking ourselves, what would you see in a neutron star? I kind of get back to Kevin's question a couple weeks ago about where does it fit on the HR diagram. So what would we see? Do we see neutron stars, and what would they look like? We'll get to that in a second. So there are some things that people see which they call neutron stars, right? And we'll talk about that in a second. But most of these supernova remnants don't have compact objects at the center, which is really, really interesting. So if I was gonna, just make a half-baked theory about what was happening in these explosions in the liquid model, I would say that those stars, for the most part, are just blown to smithereens. There's nothing left at all. Now, if there is something left, and there appears to be perhaps something left in some of these cases at least, then we have to try to make sense of what that is. All right, this just kind of summarizes this sized-based occurrence with respect to all of these things. Nice pictures of supernova. Okay, so by the way, when these supernova happen, what's kind of interesting is that these explosions do appear to be so powerful that they give us evidence of really big atoms being present. Now, the mainstream story, the one that's in your textbook, tells us that where we get all these heavy elements at the bottom of the periodic table is from the shock waves of these enormous supernova explosions. So there's so much pressure that you can actually fuse together really big atoms together and make even bigger ones. So all of our heavy, heavy elements in existence under that story come from supernova. And there's some evidence to support this possibility, at least, like I said. Let me see if I can pull up a good picture of this.
But supernova don't happen often.
What's that?
But supernova don't happen often.
They don't happen very often at all, it seems like, yeah. Now, maybe the frequency of it, maybe that is still where a lot of heavy elements come from. There are a lot of really big heavy elements, though. The question is this the only way it can happen? I don't know. But one thing that's kind of interesting, if you look at, this is a supernova explosion. See if I wrote down who this is. Oh, this is the one I was telling you about in the Magellanic Cloud, actually. It's called supernova 1987A, because it was first observed in 1987. What's really cool, though, is you kind of see these globular structures, right? And when you actually do the spectroscopy on these globular thingies, you see not only evidence for condensed matter, but you see really cool radioactive forms of heavy elements like nickel and iron. What else do we have here? Cobalt. Basically big metal globs, chunks of big metals and stuff, basically, right? Which is pretty cool. So whether that stuff derives from the stars that are exploding in the first place, or whether it's actually being formed in place, is a little bit of an open question in my book. But certainly, these big stars seem capable of producing most of the elements that we're aware of in existence. So that's kind of interesting. This is, by the way, just a light curve that shows how this is how we fingerprint and group supernovas together. This one's similar to this one's similar to that one, which is going to be important when we start talking about measuring the distance to other galaxies, because we treat them like we did with those Cepheid variables, those pulsating stars that we use to make that estimate about whether it's the semi-truck in the distance or a bicyclist up close, right? We do the same thing with supernovas to gauge really far distances. And that might be problematic because we might be confusing certain events for one another. We did that with the Cepheids. I don't know if you guys remember, but we had to actually rewrite all of our distances by a factor of 2x back in the 1950s because we had confused two types of pulsating stars for one another. So, yeah, needless to say, when we start measuring distances to things further away than our galaxy, our certainty is severely challenged and limited, really, to standard candles we can come up with. And this is the kind of fingerprinting that we would associate with those standard candles. Normally, I'd probably do a whole lecture on that, but we only got 4 classes left, so we will we'll revisit this when we get to this redshift out of distance expanding universe situation. All right, so what do we actually see? So okay, the standard astronomers have this story. These objects collapse on themselves, boom, it sets off this huge supernova thingy, and the remnant is a neutron star, right? So do we actually see neutron stars? That's kind of the next question. Well, and then this very standard mainstream answer would be sometimes, right? So sometimes we see those big clouds, hypothetically, leftover remnants of supernovas that have happened, and there's nothing at the center. It's interesting, but sometimes there is something at the center. And what is that something? Well, one of the, let's see, common somethings that's left behind is this thing called a pulsar. And what is a pulsar exactly? Well, it's basically a radiation source that's blinking really, really fast, like on the hertz frequency, so like once per second, right? Now, the standard astronomers have used these pulsars, which they do find sometimes at the center of these clouds that seem to be remnants of supernovas that have gone off in the deep past. They argue that what you're seeing is a neutron star that's basically spinning like a lighthouse really, really fast. Now, I want you to like consider exactly how fast it would be if you took something even the size of the Earth and spun it such that the Earth turned around once every second.
Fast.
Yeah. For ordinary matter, I would say a bit too fast for the imagination. Yeah.
Pretty sure the textbook says that they more commonly spin even faster than once a second. Okay.
Great. Yeah. Great. I think I'm thinking of the first one that was discovered.
Either way, it's still really fast.
Yeah, sorry. I'm actually, the number I wrote down, 1.3728 seconds, was the frequency for the first one, which was discovered in 1967 by this lady, Jocelyn Bell, who was actually a grad student at Cambridge at the time, studying, doing radio telescope analysis of distant sources. And she kind of found this one that was clocking, right? And of course, everybody jumped on it and was like, oh, it's a neutron star, right? Now, I would say that, okay, if neutron stars really are ultra-dense compact objects, they're not even made out of atoms anymore. The weird thing is that they do seem to still possess gravitational contact with their neighbors, right? So they're presumably still connected to the atoms around them. How in the world they're able to spin at hertz, maybe faster rates is a bit mind-boggling from a physical perspective, because things tend to tear themselves apart when they spin really fast.
I was gonna ask that question. I was like, wouldn't it just tear itself apart?
Yeah, it's kind of a difficult pill to swallow, like the closer you look at it, actually. Fortunately, actually, as you may have guessed, so remember we were talking about these pulsating stars back at the beginning, these Cephids, right? These are our standard candles within our galaxy, right? And I said the standard story is that, well, how do you make something bright or dim in a gaseous star? The only thing you have is radius. So the gaseous astronomers imagine that the stars are doing this, right? But in the liquid model, how do we change dimness or brightness?
It gets cooler or hotter.
Well, no, you just change the lattice structure, right?
Oh, yeah.
So for the pulsating stars, we have another mechanism as liquid astrophysicists. We can actually just change the lattice structure. We can have an oscillating lattice structure, right? Which would actually produce the same phenomenon. And the sort of chemical processes that would tune a lattice could be done really, really fast, actually, in principle. Actually, we're all aware of one of these very common ones. Where do we see this kind of thing in our everyday life?
Carbon. Oh.
Yeah, turn signals. They're the technical term for a turn signal is a relaxation oscillator. And without boring you with the electrical engineering of it, you basically have a circuit that's tuned to drive capacitance up to a point where it essentially breaks the circuit at that point. And discharges into the light bulb, and it blinks, right? So you're applying an oscillating current, which is self-sustaining based on the material resistance of the conducting species, whatever material it's made out of. And you can basically apply a current to this thing, and it will blink, all right?
Thank you for having it not be really fast.
Yeah, Yeah, but you could imagine you could do this as fast as you want. You just have to tune the resistance and the capacitance of the system. You can make as fast of a blinking turn signal as you want, right?
So yeah, that's just working by changing its lattice structure bit effectively.
It's in this case, okay, so fair enough. You're not actually changing the lattice structure of the light bulb. However, you are changing the conductivity of the circuit. You're actually changing the amount of electricity that's flowing through it. So it's a little bit of a different situation. This is fair. This isn't entirely lattice-based. However, the lattice can tune the conductivity of a circuit as well. So I'm making a little bit of an analogy here, but I am talking about material, I am talking about optics that result from changes in the conductivity. Ultimately, a lattice does have a specific conductivity, right? So let's think about this. Carbon, let's go back to our good old carbon. Graphene, right? Actually, under the right circumstances, when arranged properly, graphene's a great conductor. But diamond's a terrible conductor, actually. They're both made out of carbon. You just have two different situations, right? So the same thing could be imagined for the optics of the stars as well. So in some sense, with condensed matter, we have the ability to fine-tune these optical phenomenon using just the chemical, the conductive. I'm going to roll electrochemistry into this, right? So, you know, when I look at a neutron star or something like that, or one of these like blinking light sources, right? You know, I don't know if there's even a body there exactly, right? So if we wanted to make a relaxation oscillator and even a plasmatic gas, we could do that just by varying the conductivity of the arrangement of those molecules. This could be driven by intergalactic currents of some sort, right? You can imagine that the galaxy actually has all of the stars are in some sense knitted together with one another. There's a lot of charged species flying around. You actually have extraordinary currents going on amongst all of the stars. So there's electrical processes that might explain it. Or you might actually just have some sort of star left there that's going through some sort of cyclic oscillations in its lattice structure, which is resulting in its different emissions at a really high rate. And it doesn't require us to spin anything at incredible speeds that would boggle the imagination about how it even stays together at that point. So, okay, so we have at least a couple of possibilities on the table for these for the appearance of what we would term pulsars, which are evidence for the gaseous people. These are evidence of neutron stars. For the material science approach to this, there's a couple of other less sexy possibilities on the table, unless you think turn signals are sexy. All right, so now we approach the really, really big stars, right? So what happens when even there's too many neutrons to even resist this standard approach to gravity and everything? Yeah, either one. Go ahead. Let's get Ethan. Yeah.
They collapse into a black hole.
They collapse into a black hole.
And more specifically, a singularity, a single point of like infinite density, basically.
Yeah. All right. So this is the ultimate coup of the entire operation. This is really the point where we are told that physics stops working at some point, right? So a point of infinite density that has no size to it, right? Now, the singularity aside, the black holes are given some other architecture, right? So there's a point at which, before that singularity point, there's some radius at which light itself is said to be able to not even escape. Now, let's think about that one for a second. So the standard approach to, see if I want to come back to this actually, 1 second. I'm going to come back to it, don't worry, hold on. All right, I just want to make sure that we understand this. So the standard approach is that that at some radius, basically the light is bent back on itself. Now, light. We've talked about light a little bit in this class, right? So standard treatment of light, depending on which discipline you're in, it really depends on whether you're, a chemist or a biologist or whatever, how you treat light. But most of these disciplines treat light as this kind of magic bowling ball that just flies out of atoms. It's made out of God knows what, and it just does what it needs to do at the other end, right? I have argued, at least, I'm not sure how much time I gave it in this semester, but at least some point during this year, I've made the sort of unpopular argument that light never occurs unless there's two atoms, because it's actually an exchange of angular momentum between their surfaces, and that it's mediated by some structure that connects them. Yeah.
I think we have talked about this previously, but if you could remind me, what would that model make a photon?
So the photon would literally just be a transverse oscillation of the interconnection between the atoms in that material model. So the atoms have some extended structure. I like to just simplify it by drawing these hairs on the surface of the atom. The hairs are going to deform in a way that causes, as that wave travels down the hairs, it's actually going to jiggle the atoms at the other end, move their surfaces with the same motion that was imparted at the source atom, right? Okay, so in that conception, this don't work, right, for me, because light doesn't bend because of gravity, because light isn't a body, right? It's not a magic body that's subject to gravity, right? So why do people think that light is bent by gravity? I mean, surely the light between these fluorescent lamps above our head isn't getting pulled to the ground right now, right? Like, it would be very hard to see if it was, wouldn't it? Yeah.
Is it because the light from certain objects is like distorted in a way?
Yeah, and where do, is there any evidence for this? Yeah, Kevin.
I'm not entirely sure, but I think I did hear something about how the sun itself actually can warps sunlight. Like if you are able to look very, very closely at the surface, it's like barely there.
Yeah, go ahead.
I mean, I can only imagine, given just how common the belief that immense gravity bends light, there must be something.
Yeah.
Some amount of evidence for that. And there is some memory in my head that, for all I know, isn't an actual memory, that it like images of like or observations of stars changed given the position of the Earth in its orbit around the sun.
Yeah. There's a couple of these things. So first of all, the concept of mass, I've kind of picked at it a little bit, right? So photons have momentum to them. This is kind of the confusing thing, right? So the concept of I'm going to try to keep this as low level as humanly possible, but we have to deal with some of these concepts because we need to understand why in the world people think that gravity bends light in the first place. If gravity didn't bend light, these black hole things wouldn't make any sense anyways, for other reasons than the fact that physics breaks down. So this all kind of starts with the idea, I mean, I hate to blame this on Einstein, but it kind of goes back to Einstein, who prepared this really magnificent mathematical piece in two parts called relativity. And relativity acknowledges that photons have momentum, right? They do. You can actually I've mentioned this before, you can push sails in outer space with light, right? Now that makes sense from where I'm sitting under the model that I just gave you guys for how I think light works. I think that you're actually sending a physical wave down a material, which is actually going to lead to a kick at the other end. So that makes perfect sense to me. The problem is this concept of mass is sort of ill-defined in physics, right? Is it the amount of stuff that's there? Is it a gravitational phenomenon? Do particles, does the proton have mass? Like, what does that even mean? You go look at it, it turns out that, well, you don't actually weigh a proton on a scale. You just see how much electromagnetism you need to apply to bend basically a column of these ionized, I'm going to call them ionized atoms, but you can call them particles too. So it's an equivalent mass, right? It's an equivalent effort to mass. And so the word mass gets really messed up. What I'm trying to get at is that in order for the photon to have momentum, momentum is literally defined as mass times velocity. That means that the photon ends up with a mass, which is very confusing because, well, the light particles aren't like bouncing off each other and falling on the floor. So if you define mass as the amount of stuff that's there, then why the heck aren't the photons piling up all over the place, these little balls of whatever, right? That doesn't really make a lot of sense. Needless to say, this wasn't sorted out by the time Einstein made his general theory of relativity. And as a result of that, the photons have mass, and anything with mass is subject to gravity. So it's a postulate, let's say it's sort of baked into the cake of general relativity, that light should be bent by large, big bodies, right? And so one of the first tests of relativity, which was championed by Einstein's great supporter, Arthur Eddington, who's come up a couple of times in this class, was to go at one of the eclipses in the early 20th century and try to measure the position of stars near the sun. And lo and behold, the positions of these stars appeared to have shifted when they were in the near vicinity of the stars. So everybody was like, great, light is bent by gravity. And then, you know, sort of what do they say? The cat was out of the bag at that point, right? And so now pretty much any time that we see optical distortions associated with path travel near stars, the gaseous astronomers chalk it up to gravity, right? There's some problems with this, though. So let's go back to this. All right, so all right, I'll work my way to that, but I want to pause for a second. So, general relativity. This is the thing. Like every high school science class has a picture of Einstein's face on the wall. Everybody's so proud of this piece of mathematics, right? I mean, Einstein was brilliant. I have a tremendous amount of respect for the guy. Long before he did this relativity thing, he basically solved some problems about what heat really means concerning the motion of atoms. He realized that light could generate electricity when shown onto surfaces, which is basically how our solar panels work at this point, right? He nailed a bunch of really cool physical stuff before he got into this mathematics stuff. But what he did was he came up with a theory that related inertial mass to gravitational mass, right? So the idea, you basically set those two Newtonian equations equal to each other, the gravitational one and the F equals ma inertial one, and processed it to its full logical extent to show how different bodies would behave with respect to one another, essentially in a field-based approach. So a way of essentially showing this kind of thing, where you basically model space, so distances between bodies essentially, and you show what would be the expected trajectory at each point. And it's extremely precise, actually. Now, does it really improve upon our gravitational orbital mechanics that we get from Newton? Not really, a little bit, but it's not enough that NASA uses it for their space launches to other planets or anything like that. They still use the Newtonian approach, which is perfectly fine for almost everything. And we talked about this whole elevator experiment thing too. This is the equivalence between the inertial and the gravitational ideas of mass. The problem is with relativity, not that relativity isn't extremely accurate, right? The problem is, does it actually tell us anything mechanistic about what's happening? So this is a fun paper I found by this Greek philosopher. And
Modern Greek philosopher.
yeah. I tried to get in touch with this guy, but I don't think he speaks English. So it didn't work out. But he sort of parodies general relativity and sort of the modern mathematical approach to physics as being something like watching a magic show without talking to the magician. So let's say you go to a theater. Has anybody ever seen Peter Pan in a theater before? Yeah, I think I have too, actually, way back in the day. Pretty cool, right? So Peter Pan's flying around on stage and everything, right? Now, let's say that everybody has a camera in the audience, a video camera, and everybody takes their perspective, and you take all this footage, and you reconstruct a beautiful 3D simulation of what was happening on the stage. So you see Peter Pan flying from every single perspective, and you reconstruct it very accurately. And let's say you encode that in mathematics. What you would have basically done is assembled a relativistic perspective of what was occurring. You have everybody's perspective from every angle looking at what's happening, right? And you say, hey, we know for sure, from every perspective possible, we can model it precisely that Peter Pan flew from one side of the stage to the other. It's proven that Peter Pan can fly, right? Well, what's the problem with that? Yeah.
Peter Pan obviously doesn't fly because the right. And if you just went to the production, right, and asked them, you would know.
Yeah, maybe even if you were able to have, maybe if you had a really good lens or something, you might even see the little cables attached to Peter Pan, right? But maybe those eluded you. Maybe you didn't see the cables that were attaching the flying actor, right? So you have this incredibly precise mathematical formula now that tells you exactly how the guy or lady, whoever's playing Peter Pan, is flying across the stage. But it doesn't tell you anything about the mechanism for how it happens. That's the essential crux of the modern mathematical approach to gravitating bodies that we get from relativity. Yeah.
So just brief contextual
Yeah.
words. The current scientific body of understanding around relativity has been making a bunch of assumptions and math to find how it looks like the way it does.
Exactly. Exactly. And so the problem with that is you don't ever have to ask yourself what light is at all, as long as you can make really accurate predictions of how it behaves, right? And so therefore, when we start trying to make sense of things like the bending of light, we don't really have to understand what it is that causes light to bend. In fact, even for basic materials, like, I don't know if you've ever stuck a pencil into half a glass of water, but it bends the pencil, right? I mean, the pencil looks like it bends when it's in there. Now, you go starting to ask questions, you get a little bit deeper than the textbook explanation for that. You're going to run into serious problems about the question as to what light really is and what's really causing those rays to be reoriented in the particular way that they are. So again, the mathematics that we have, and I do think that relativity is in some sense proved to be a pretty extraordinary piece of mathematics that makes really tight predictions about many things. It doesn't offer anything in the way of cause, right? So we don't ever get to anything close to why Peter Pan appears to be flying across the stage. All we can say is that Peter Pan moves across the stage, and we can say exactly with high precision how fast, how predictably Peter Pan's going to move across the stage, right? So it leaves the wires out of the story, which is really, really critical to our analysis of what's happening here. Okay, so we see something like this. We see objects going around one another, and we can sort of make the leap and say, well, we know that objects move this certain way around one another based on their masses. Well, we've known that since Newton's time. We really haven't gotten any better since then. It's much more precise now. Now, the popular science media and so forth, and by the way, Einstein kind of abhorred people doing this, but they basically have turned this coordinate system into a pseudo-substance they call space-time, right? So what the heck is that? Is it actually a material substance? Space-time? No, it's just a set of coordinates. It's like movie frames in a story, right? But you turn it into a sort of pseudo goop like this and try to communicate to the public how these complex mathematics have some approximation to an they have some approximation to an explanation. But they don't actually. They don't at all. It's really just a coordinate system of predictions. Very similar to when Newton first said that, hey, the amount of material he called mass at the time really scaled the orbital dynamics, right? It told you how fast something was going to rotate around another thing. That's essentially where we're still at. Now, as to this business of whether light actually is bent by gravity, this is a really interesting question. So, refresh my memory with what we have here. All right, so this is basically the experiment that was done at the eclipses, right? And the idea was that, light from a distant star would pass by. It will actually be sort of curved around, so its apparent position will move relative to where it was before the sun was kind of converging on the path of those rays, right? Now, this does appear to have been done, but there are some interesting pieces of the puzzle here. There's some actually pretty damning pieces of this puzzle that have arisen since this original Eddington experiment, which was, did I write down when that was? 1919 was the original experiment. All right, so what's happened since then? Well, one thing that's happened is that we now realize that you can model how much light should be bent by a star. And it's actually a pretty diffuse interaction. So as you might imagine, the gravity falls off. The intensity of the gravitational field, as it would be called in the relativistic convention, it falls off with a very particular distribution, which is actually called a Gaussian. I don't know if you guys ever encountered that in your digital media, but it's a particular bell curve type thing where some effect falls off from a point source, right? Now, the weird thing is that the Gaussian distribution of the intensity of the gravitational flux, basically the effect of the gravity, should fall off with this particular distribution. The problem is that we actually have never seen any starlight bent outside of a very tiny piece of distance beyond the limb of the sun, the outside of the sun. So we actually have only seen those star effects while they are essentially inside of the corona of the sun, right? So that light is actually shining through some sort of gaseous medium where we see the bending of it. And where we should still see the bending of it beyond the corona of the sun, we don't see any bending of the stars, according to the gravitational formulas. Yeah.
Yeah, when you asked about why does the light bend the pencil in the water glass, my thought was, well, with the material explanation, it's just the lattice. It's getting, it's getting bent in different directions. It's not a straight line. It's
Yeah.
bent in weird ways, and then data's lost or distorted by the time it reaches.
Yeah, maybe you guys have actually seen this kind of thing. That's true for a liquid. I'm going to assume that the corona of the I agree the corona of the star is obviously a gas. Can you guys think of times when gases bend the path of light? Especially hot ones? Yeah. Smoke. Smoke's got a lot of dust and condensed matter in it. Yeah.
Immediately when you said heat, go to it.
Yeah.
I see it here on a hot day.
Yeah.
Look at asphalt. You look
Yeah.
at what looks like a puddle of water.
Yeah.
Or the good old heat wave.
Yeah. Have you guys ever? Yeah. Go ahead.
Thinking of what's emitted from barbecues.
Yeah. Yeah. Exactly. Yeah. So mirages, basically, stuff like that, right? So gases do a great job of lensing light, actually, especially heated gases where you have a density differential. Density is really what it is inside of those mirages because the heated air is taking up more volume than the colder air, right? It's bouncing around more. All right, so we don't need any kind of magic to bend light using gases. The corona of the sun is obviously a gas. We know that because it has discrete line bands and so forth. Plus, it just looks like a gas. Let's be honest, if you've ever seen an eclipse, you can see this stuff dancing around. It looks like a flame, because it is. So that's really interesting, and nobody, to my knowledge, has followed up on this. Actually, the guy who wrote this paper is a former NASA scientist. He unfortunately just passed away, which I'm terribly bummed out about because I really wanted to get this guy on my podcast. He's the only person I know of who's written a paper about this, and he points out a few things. So he points at, the fact that there isn't actual bending of light from stars in that Gaussian distribution beyond, I think, 1 or 2 solar radii, which is essentially the corona to which extent the flames of the outer part of the sun reach out to. He also points at, one of the things that the gaseous astronomers love to talk about is these things they call Einstein rings, right? Which are basically these, and you might have seen these in the Hubble Deep Field images, where you actually see these like distorted little, you see a star and you see like other stars kind of bent around it, like they're actually lensed, right? And he attacks this in this same paper too, saying, well, first of all, stars have more than ample ability to lens light without having to do anything with gravity based on this discussion we've just had. But also that there's plenty of stars that are exactly in line with the sources behind them that don't appear to be bending the light behind them. So it's a completely inconsistently applied idea, right? Why in the world don't we just look out into the night sky and just see like warped stuff everywhere? Because there's huge stars everywhere. So we literally shouldn't be able to see anything that's not just like a complete, psychedelic nightmare, because none of this light should be reaching us undistorted if this is the case. And then he also attacks something that we haven't gotten to yet, we'll get to soon, which is that we're supposed to have a supermassive black hole at the center of our galaxy. If that were the case, why isn't it bending the heck out of all of the light that we see coming from the center of the galaxy? It certainly is not. You can resolve stars very close to that center point with no issue whatsoever. So, does gravity bend light? I am not convinced that it does, and I can't mechanically explain how it would, even if it did. Now, there are some interesting effects, right? So stars definitely do seem to bend light near their limbs sometimes, at least our star does. Could that be explained by some sort of density distribution in the gaseous atmosphere? I think it could. There's other interesting effects too, like if we look at there was some studies done. This is called Shapiro. A guy named Shapiro did these studies. We'd actually send these sort of like when the cops are trying to give you speeding tickets and they shoot a radar beam off of you. He did this with Mars as it was kind of passing near the sun. And he showed actually that there was some delay in the signal as it came back, right? As it kind of passed back, or I guess it's a two-way signal, but there's some delay in that. Now, again, if there's lots of material in the way, you might actually have a means by which those relay processes could deform the path of your or elongate the path of your travel as it went through all of that. So I'm not sure that that has anything to do with the bending of time itself or anything crazy like that either. So when we start thinking about these black holes and their primary attribute, which is the ability to bend light and eat light and swallow light, and this is what causes them to be black in the first place, we have some serious problems on first principles alone. Now, are there places in the sky where objects appear to be orbiting nothing that generally are getting chalked up to black holes? There absolutely are. There are definitely points in the sky where there are luminous stars orbiting something that we can't see. But does that have to be a black hole? Does it have to be a place where physics breaks down? I don't think so. I think that we have to reach a bit further. Again, if all you have is gas to try to tell this whole story, yeah, maybe you do end up having to break physics to finish your story. But if you have actual materials that are interacting and have optical properties and have conductive properties that reflect the arrangement of their structure, of how their atoms are structured and bound together, then you run into situations where you might be able to explain that with pretty ordinary, boring stuff that just isn't luminous anymore. So
I was thinking initially, what first pops in my head is binary systems, where where two stars are orbiting a single point, and there's nothing there.
yep.
They're just orbiting each other.
And that might be a great explanation for what is generally termed supermassive black holes at the center of galaxies, right? Because there's a lot of stars on either side of that pinwheel that are all pulling on each other, and they're shared the technical term is barycenter, so it's where their masses would meet. It's where their gravitational influence would meet. For some of these stellar mass black hole thingies, where we just see a star orbiting what would otherwise just be a regular star, so their orbital mechanics are normal. It's like there's a star there, but we can't see it. Well, we might be dealing with one of our Vasco blinked out stars at that point. You might be dealing with something that's still pretty chunky. It's just no longer luminous the way that we would expect it to be. That's a serious possibility.
So,
It could be even quite old and cold and invisible at that point. Yeah.
So it's just kind of like a black dwarf or something.
or black giants.
Yeah, or even yeah, I guess brown would be too hot, but something colder. Yeah, really cold. Yeah.
So in other words, a dead star, old.
Yeah. I don't like the dead thing though, because I'm like, man, if Jupiter's a dead star, it's still living its best life, you know what I mean?
Still got heat and emits light.
Yeah, yeah. Well, but even if Earth doesn't emit a ton of light, maybe a bit of infrared, but still, we got a lot going on here still to call ourselves dead if that turns out to be the ultimate natural history of this place. All right, so I think that tees us up for moving into talking about galaxies. I don't know. Think about it over the weekend, guys, and we'll review all this on Tuesday. But have a good one. Good luck with all of your crushing ends of term business, and yeah, thank you.